So this is going to be a calculator question. We are going to do as much stuff as we can without our calculator to practice that, but there will be some things that we'll need to use our calculator for. Sometimes when you're asked to graph something and it is on a calculator part of the exam, then if it's an exam, unless it specifically says to show certain parts, you can just use your graphing calculator to get those parts of your graph, to label your maximums and your minimums. Now, for this function, they give us a specific domain. So we want to graph this from 0 to 5 pi over 2. So the first thing, when a domain is given, you will also have to label your endpoints. So when we're going to sketch this, we're going to want to label what happens at the endpoints of our domain. In other words, what happens when x is 0? And what happens when x is 5 pi over 2? So do a little bit of mental math. Plug in 0. What do you get? Plug in 5 pi over 2. What do you get? We're going to get 0, 1, because e to the 0 is 1, and cos of 0 is 1, and 1 times 1 is 1. Now, if you're doing the 5 pi over 2, okay, and you're stuck in the mental math because you work from left to right, and you're desperately trying to do e to the power of negative 5 pi over 2 in your head, then take a step back and try cos of 5 pi over 2 first. Cos of 5 pi over 2 is 0. Okay. So now 0 times anything will be 0. That'll make things easier than you're not having to calculate. I'm sure some of you are probably already at 5 decimal places of e to the negative 5 pi over 2, and we're close to feeling like you could store that in your memory and then multiply it by cos of 5 pi over 2. But that is a strategy. Try to figure out, is there something easier I can do mental math first, and maybe that makes the whole thing simpler. So now we want to find our exact values of our x-intercepts. X-intercepts are when y is equal to 0. And we have e to the negative x times cos of x. We have two things here. In fact, we have to check, if I split things up here, we have to check either when e to the negative x is 0 or when cos of x is 0. Now, e to the negative x, if you think of it graphically, what does e to the negative x look like? It is an e to the x graph flipped over the y-axis. It'll go through the point 0, 1. It will have an asymptote here at y equals 0. If that's my graph of y equals e to the negative x, does it make sense that this side here is never 0? It's always positive. Not only is it never 0, we can also make a note that it's always greater than 0, or always positive. Now, thinking of cos x, when is cos x equal to 0? Well, we go to a unit circle, and we say, I know that cos x is equal to 0 at pi over 2, 3 pi over 2. If you kept going around, you'd hit 5 pi over 2. Of course, that's as far as we would need to go. So the exact values of the x-intercepts are at pi over 2, 3 pi over 2, and 5 pi over 2. So far, we have our x-intercepts and we have our endpoints. Now we want to find the coordinates of the first two stationary points. Remember, we find stationary points. Those are maximums, minimums, or stationary points of inflection with our first derivative. So for part B, I'm going to need to find my first derivative. It's going to be a product rule. If I use the product rule, keep the first one the same, multiply by the derivative of the second one. The derivative of cos is negative sine. Plus, keep the second one the same, multiplied by the derivative of the first one. The derivative of e to the negative x would be e to the negative x times the negative 1, because there would be a chain rule. Now, when going about solving this, right, because in order to find our stationary points, we set our derivative equal to 0. Notice you can factor an e to the negative x out. That will leave you with negative sine x plus cos x, or cos x minus sine x. Oh, actually it will be, here, I'll write it out. This will have a negative sine x. When we factor that out, we are still left with a negative cos x because of the negative 1. So when this is equal to 0, if we split it up here, either e to the x equals 0, which we already figured out that this is never 0 from before, or this is equal to 0. In other words, when is negative sine x equal to cos x? Now, when you get these questions which negative sine x minus cos x equal to 0, in other words, when is sine x equal to cos x, or negative sine x equal to cos x, either you can think about your pi plate and figure it out directly. Think about when are sine and cos equal? Pi over 4 family, right? They're both root 2 over 2. So we need one of them to be positive and one of them to be negative here. So you could think about your unit circle and where that happens. The easier way to do a question that has a sine equal to a cos is if you divide both sides by cos, this becomes tan. If I multiply by a negative, it's really asking when is tan equal to negative 1. That is a little bit easier than thinking when is sine and cos the same, but one is positive and one is negative. Because now it's just asking when is tan equal to negative 1. It's still pi over 4 family, but tan is negative in quadrant 2 and quadrant 4. If you think about your unit circle, in quadrant 2, you've got the coordinates negative root 2 over 2, root 2 over 2. In quadrant 4, you have root 2 over 2, negative root 2 over 2. So you have the sine and the cos are the same, and one is positive and one is negative. If we now go about listing when those happen, in quadrant 2, you would have 3 pi over 4. In quadrant 4, you would have 7 pi over 4. And the question asked only for the first 2 stationary points. So we would have found the x coordinates of the first 2 stationary points. To find the complete coordinates, well, a couple things here. I'm going to draw my number line, and I'm going to have 3 pi over 4 and 7 pi over 4 on here. I'm going to add my endpoints of 0 and 5 pi over 2 to find out where things are increasing and decreasing. So something between 0 and 3 pi over 4 would be pi over 2. What happens when I plug in pi over 2 into this equation? Well, another thing we also made a note of is that e to the negative x was always greater than 0, so this section is always positive. If I plug in pi over 2, sine of pi over 2 is 1, cos of pi over 2 is 0. Can you see that if sine of pi over 2 is 1, I'm going to get a negative 1 inside of the brackets here? And a negative 1 times a positive number is going to be negative, so this part of my graph will be decreasing. Between 3 pi over 4 and 7 pi over 4, a very easy pi plate value, unit circle value to use would be pi. If you plug pi in, sine of pi is 0, cos of pi is a negative 1, minus a negative 1 will be a positive 1, positive times a positive, this section will be positive, and our graph will be increasing. And finally, if I choose something between 7 pi over 4 and And 5 pi over 2, I'd probably choose 2 pi. Sine of 2 pi is 0. Cos of 2 pi is 1. This will be negative. A negative times a positive is negative again, so this will be decreasing. So we now know, oops, that's a really big bracket. 3 pi over 4 comma something is our minimum, local minimum, and 7 pi over 4 comma something is going to be a local maximum. And to find out those values, we would plug that back into our original equation. So our original equation up here was e to the negative x times cos x. So if I go to my calculator, I am going to type that in, e to the power of negative x multiplied by cos x. Make sure that my mode is in radians. It is. I'm going to go to my window and set my x min to negative 0.5, my maximum to 5 pi over 2. And I'm going to hit graph, not worrying about anything else right now. Wonderful. So we wanted to find out what these values were at 3 pi over 4 and 7 pi over 4. One way you could do that is you could type in your equation here in your regular window and say e to the power of negative 3 pi over 4 multiplied by cos of 3 pi over 4, and figure out that it's the y coordinate will be negative 0.67. So I'll write that in, negative 0.067. So we could find it out by plugging that value in, and that is a little bit annoying because you have to type a lot to get it in. And I've already typed it into my graph. So on my graph, if you go second calculate, there's an option number 1 that says value. And what that'll do is let you type in any value for x you want and find it on your graph. So if I would have done it this way, all I would have had to type in is 3 pi divided by 4, and it would also tell me negative decimal 0.067, a little bit quicker. And the nice thing about this is once you find one, you can just type in your second one. So the other one we want to find out is 7 pi over 4. It'll find that one as well, 0.0032890. 0.00289. Is that rounded correctly? No, 290. Max. So we have now our minimums and our maximums. We needed our calculator to get those y coordinates. Those aren't mental math kind of coordinates that you could figure out. Now, as far as graphing this goes, one pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. As far as graphing things go, I've got a scale set up there. I'm going to put, based on what I've noticed with my max and my min, and I already know my endpoints, I'd figured out that one endpoint was at 5 pi over 2 comma 0. I figured out that pi over 2 and 3 pi over 2 were my x-intercepts, and I knew that 0 comma 1 was my endpoint over there. Now, on my graph, I'm going to need to label 3 pi over 4 and 7 pi over 4. And label those points on my graph as well. What happens at 3 pi over 4? I'm actually going to move this to label above. .67. That would approximately be about there. 3 pi over 4, comma, negative 0.067. And 7 pi over 4 is at 0.00290. That's going to be really close to the x-axis. So if I label that point, now, what do we know about our graph? We know that it's decreasing until 3 pi over 4, increasing until 7 pi over 4, and then decreasing again until we're done. So as far as our final graph will be, we're going to be decreasing until here. It's going to go through this x-intercept to maximum there, and then back down to 5 pi over 2. These max and mins, when we graphed it originally, if we look back at our graph on our graphing calculator, we can't even see those max and mins. If I wanted to see those max and mins a little bit better, I might go to my window. I don't need to go up to 4. Maybe I'll go up to 1 because I know that that's my maximum anyways. And my y min, I don't have to go lower than 0.067. So maybe I'll go negative 0.1. And I'm going to hit graph and see if we can see that max and that min a little bit better from our graph. Boy. I would say yes to being able to see the minimum. Can you see the maximum? No, not really. So if we wanted to, we could zoom in. There's a way that you can use your arrow keys to zoom in better. Okay, that was not how to use your arrow keys to zoom in better. Look at that wonderful graph. Ah. Yeah, so that was not a good use of zooming in better. There, we're on a value now, but you still can't see it. Zoom. There we go. Zoom back out. I'm going to try to get to this maximum, which is about there. And now I'm going to try that zoom in. Now that it's on that point. Oh, can you see the maximum? Definitely somewhere along that straight line there was a maximum. Okay, so this one was, as far as the graphing goes, okay, I like this as a mix of needing your calculator and not needing your calculator. For one, the calculus let us know that there was a maximum there and a minimum there, and we could do that and find the x-coordinates of the max and min without our calculator. It was only when we needed our y-coordinate that we needed our calculator. If you just went to your calculator, the line looked really straight. It was actually quite hard to see that max and that min. So you might have missed those from your calculator. So it's a good use of needing your calculator and not needing your calculator. Okay, I'm going to get one more graph one. This one, do you notice that we didn't find this point right here? Somewhere there would have been an inflection point. We would have to do our second derivative and do that, but the question didn't ask us to find that inflection point. But for this next question, we want to do everything. We want to find all of our stationary points, all of our inflection points. This does not look like it's an easy one to find x-intercepts, but you can label your y-intercept. Find out where it's concave up, where it's concave down, where it's increasing, where it's decreasing, and sketch the entire graph. So I'm going to give that to you. I'll put up the first little bit so you can check how you're doing so far. There's your y-intercept. There's your first derivative. Again, once you find the x-coordinates, you find the y-coordinates of your max and your min by plugging back into your original equation. And here's your second derivative for finding your inflection point. And then putting those on your graph, that is what you will get. This 0, -5 is not the x-intercept. That's 0, -5. That's your y-intercept there. Those red points that are x-intercepts, you would need to use your graphing calculator to find them. This isn't one that is easy to factor. So we're wanting to graph the graph of x to the 2/3 minus, well, 3 times x to the 2/3 minus x. We're going to find all stationary points, all inflection points, indicate where the graph is concave up and concave down. So very similar to what we've done before. Also in this one, we could attempt to find our x-intercepts as well. But let's start with just finding our stationary points. So to find our stationary points, we would need to find our, well, for our first derivative. So let's find our first derivative. Our first derivative, the 2/3 would come out in front. That would just be a 2. Subtract 1 from the exponent, -1/3 minus 1. If we make this equal to 0, we would have 2 over the cube root of x minus 1. How do I solve an equation like this? Well, I'd like to get rid of that fraction. I'm going to move the 1 over to the other side. And then if I multiply both sides by the cube root of x, I get the cube root of x is equal to 2. How do you get rid of a cube root? Cube. So if we cube both sides, we're going to get x equal to 8. So when we go to our number line, what are all the things that we include on our number line? We include our critical point where it's equal to 0, so that's at 8. What else do we include on our number line? Any non-permissible values. Now, our original equation, does it have any non-permissible values? No. But our derivative does. What's our non-permissible value for our derivative? 0. So we'll also have to add 0 onto here. And this, I'm guessing for all of you, is the first time ever you've seen a graph where there's a non-permissible value in the derivative that isn't a non-permissible value in your original function. In fact, in your original function, if you plug in 0 for x, what do you get for y? 0. So it's a point that actually exists, 0, 0. So we're going to find out what happens at that point, because the derivative doesn't exist at that point. So we can't draw a tangent at 0, even though there's a point at 0. Okay, so now that we've got our number line there, we can do our regular check. What happens when you plug in something less than 0, like a negative number? Like if I plugged in -8, this is going to be square root of -8, or cube root of -8 is -2. So I'd have -1 minus -1 will still be negative. Our graph is decreasing. Between 0 and 8, so if I chose something like 4, the cube root of 4 is a little bit more than 1, but less than 2. So 2 over something between 1 and 2 is going to be a little bit bigger than 1. 1 minus 1, something a little bit bigger than 1 minus 1 will still be positive. This part is increasing. So it appears that at 0, we might have a minimum. And then after 8, if you choose something after 8, like the square root of 27, this will be 3 on the bottom. 2/3 minus 1 will be negative. It's decreasing again. Okay, there's our first derivative. Now, change colors here. If we go to find our second derivative, the derivative of second derivative, the -1/3 would come out in front, making -2/3. Subtract 1 from the exponent would give you -4/3. As far as what's happening at this point, this is the same as -2 over 3 to the cube root of x to the 4. When we go to make our number line, this is never equal to 0, but it has a non-permissible value at 0. However, anything that you plug into this graph, no matter what you plug into this graph, can you see that the bottom is always going to be positive? And the top is negative. So these will both be concave down. All right, we will complete this graph tomorrow. It's so exciting what's going to happen at 0, but you're going to have to wait.